Okay, so I asked you to do the questions on page 622, starting with number 9, and you're going to need the half-life table back on page 621. So 9 says, a sample of 1 gram of tritium, so your initial mass is 1 gram, is produced. What would be the mass of tritium remaining after 24.6 days? So the 24.6 days is the full time that passes. Except I don't think it's days, it's years. It is years. And they want to know the final mass. And if you go back to the chart, you can find that the half-life of tritium is 12.3 years. So the first step is to figure out how many half-lives. So the other video I showed you that n is just equal to the full time divided by the time for 1. So 24.6 over 12.3. Higher order math, but hopefully you get 2. So then you want MF, and we know MF is equal to MI over 2 to the n. So 1 gram over 2 to the 2. 2 to the 2 is about 4. 1 over 4 is a quarter. Final mass will be 0.25 grams. You could have also said, okay, if there's 2 half-lives, in the first half-life there'd be 0.5 left, and the second half-life there'd be 0.25 left. But in physics, we usually do like to see a little bit of work. All right, the isotope of neptunium-278 has a half-life of 2 days. So it's telling us T1/2 is 2 days. 4 grams were produced on Monday. So Mi is 4 grams. What'll be the mass of neptunium remaining on Tuesday of the next week? Tuesday of the next week, that would be 8 days away. And it wants to know what's MF. Okay, so again, first find your n, delta t over t of 1/2. So 8 days over 2 days. Again, complicated math, but n should be 4. So then you go MF is equal to MI over 2 to the n. So 4 grams over 2 to the 4th. 2, 4, 8, 16, 4 over 16. MF, again, is equal to 0.25 grams. Number 10. Number 11. A sample of polonium-110 is purchased for a physics lab on September 1st. Its activity is 2 times 10 to the 6 decays per second. So the initial activity, 2 times 10 to the 6 decays per second. I'll write it like that. The sample is used in an experiment on June 1st. Okay, so the time, it's bought on September 1st, and it's used on June 1st. 30 days has September, April, June, and November. All the rest is 31 except February. Okay, so you have to add it up. 30 for September, 31 for October, 30 for November, 31 for December, 31 for January, 28 for February, 31 for March, 30 for April, and 31 for May. So you should get 273, I think that is. 273 days. If you go and look up the half-life, you will find the T in the chart, you'll find it's 138 days. Okay, so n will equal delta t over t1/2. So 273 over 138 does not go in evenly, unfortunately. 1.978. And so then when you do, it's activities, AF is equal to AI over 2 to the n. It'll be 2 times 10 to the 6 decays per second over 2 to the 1.978. And when you do this, you should get 5.0759 times 10 to the 5th decays per second. Okay? So again, remember, it doesn't matter if it's decays or mass or counts. You're going to treat them all the same. Number 12. Tritium, hydrogen 3, was once used in some watches to produce fluorescent glow so the watch could be read in the dark. If the brightness of the glow is proportional to the activity of tritium, what would be the brightness of the watch in comparison to its original brightness when the watch is 6 years old? So delta T is 6 years, and when you look up the half-life of tritium, we already used it in question 9. It's 12.3 years. And so number of half-lives, delta T over T1/2, 6 years over 12.3 years, N is going to equal 0.4878. And so now we're looking for brightness, so maybe I'll use BF, which is equal to BI over 2 to the N. And the question wants to know what would be the brightness of the watch in comparison to its original. So you could write it as BF over BI, right, in comparison to its original. And that's going to be 1 over 2 to the 0.4878 out of paper. And when you do this, you discover that it is, I think, 0.7131. Okay? That's the ratio. All right, then I asked you to flip over a few pages and to do numbers 12 to 15. This was on page 637. So number 12 says, in an accident in a research lab, a radioactive isotope with a half-life of 3 days, so T1/2 is 3 days, is spilled. As a result, the radiation is 8 times the maximum permissible amount. So the radiation, we could call it Ri, is 8 times the permissible amount. So when you start, it's like 8x, and you can only go back into the lab when you get down to x. Okay? And so it wants to know how long before they can enter the room. So first you need to know how many half-lives have to pass. So RF is equal to Ri over 2 to the n, and you're rearranging for n. So 2 to the n is equal to Ri over Rf, which is like 8x over x. So 2 to the n is equal to 8. And hopefully you know 8 is 2 to the 3, so therefore n is equal to 3. So then you say, okay, so n is equal to delta t over t to the 1/2. So delta t is equal to n times the half-life. So 3 times 3 days, you need to wait 9 days before you can go back inside. Okay? Number 13 says, if the half-life of an isotope is 2 years, so T1/2 is 2 years, what fraction of the isotope remains after 6 years? Delta T is 6 years. So again, n is equal to delta T over T1/2. Hopefully you get about 3 there. So you want what fraction? So MF is equal to MI over 2 to the n. So the fraction, MF over MI, right, that's the fraction that'll be left, is equal 1 over 2 to the n, or 1 over 2 to the 3, or 1/8. So there'll be 1/8 left after 6 years. Okay? Oops, already written on. That was number 13. Number 14, the half-life of strontium-90 is 28 years. So T1/2, 28 years. Shoot, I'm going to run out of time. After 280 years, so delta T is 280 years, and hopefully you can see that n is going to be 10. What would the intensity of the sample, the strontium-90, compared to the original? So intensity final is equal to intensity initial over 2 to the n, and you want the ratio of the final to the initial, so that's just going to be 1 over 2 to the n. So 1 over 2 to the 10th. So